Hi, so let's talk a little about weight initialization. So what do I mean by weight initialization? Right, so I think we've done this a little bit. If you paid attention in our week 1 assignment, we initialized our initial weights when we were doing this linear classifier before we started the gradient descent, and we initialized it just to random values. But let's say we create a neural network, right? Let's say we have a neural network like this where we have these 3 different layers, right? So you have your input layer, so there's a matrix here, and then you have your output. So we have these 2 weight matrices, right? And we have an input of size 4 and we have also an output of size 4, and we have some hidden layer. And now what we need to do is we need to initialize all these weights, and what I'm saying is let's initialize it with 0, right? So what do you think will happen if we initialize the weights with 0? So what will happen is that it will kind of get stuck because the update for each neuron will be the same. What will happen is your loss, when you back propagate it, there will be no symmetry breaking. Each weight will go in the same direction and it will never converge, right? So this is what happens when you use W equal to 0. You should try it, especially for like a neural network with 2 layers, and you will very quickly see what actually happens. Now let's try the other idea that we used in the assignment. So very small random numbers, right? So let's say we sample from a small Gaussian with mean 0, sigma 1. So you know what our Gaussian distribution looks like. It will look something like this, right? It'll almost be 0 at say -3, because you know the 3 sigma, the 95 plus percentile happens at 3, and because the sigma is 1, it will happen at -3 and +3, and we then scale it. We scale it by in this range from -0.01, so we multiply it with this 0.01, right? We do the same to your weights and to the bias. And what you will notice when you do this is that it works okay for small networks like our 1 layer CFAR 10 classifier, which we did in the week 1 assignment. But it can lead to non-homogeneous distribution of activations across the layers of a network. And that is what I mean by the symmetry breaking, and I recommend you to try it. So now let's look at some statistics, right? Let's kind of do this for a 10 layer neural network, each with 1000 neurons on each layer, and using Tanh as the nonlinearity, and initialization as we did it in the last slide, right? So we will do this initialization where we will sample from this Gaussian of mean 0 and sigma 1, and then we will scale it by 0.01. And then we're creating this neural network, right? So our neural network looks like this. Our input is these 1000 numbers, and our input, as you see, is also from let's say Gaussian distribution, and each linear layer is of 1000 neurons and it goes to 1000 neurons, right? So what does our neural network look like? Our neural network looks like these 1000 neurons, so it's 1000 cross 1, and then the neural network is essentially like a flat neural network, right? So you have these many layers. So in this case we have these 10 layers, and each also, let's say dot dot dot, and finally we also have these 1000 neurons as output, and each of them is 1000 cross 1, right? So 1000 cross 1, and again 1000 cross 1. And now what we want to do is we want to take our random Gaussian distributed input, and then we want to essentially, we have our linear layer, and we use the same linear layer, and we basically get the hidden out, right? So we get the output of this layer, and then we put it as input to this layer. We get the output and then we put it as input. Similarly, we get output here and put it into the last layer. And what we now want to do is we want to look at the statistics of the activations of all these layers. So let's see what happens when we actually do this. And we will give you this as one of the notebooks that you can run so that you get to see for yourself that what I'm saying is indeed true. And like actually doing is when the learning happens. It's good to know what I'm saying, but it's the exercises and it's the assignments and it's the notebooks that you run which will make this information yours forever. Yeah, so we had that network, that 10-layer neural network with those 1,000 neurons each, and the initial input was nicely distributed, and then this is the output of, say, the first layer, right? And you see the first layer, so we had a nice looking Gaussian as input because we created our data like that, so all the way from +3 to -3 with a 0. But now when we put it into this neural network where we had scaled our weights to this with this 0.01, and but we had still distributed it around 0, so minus, let's say, 0.01 to plus 0.01 or minus 0.03 to plus 0.03, because it's a Gaussian, so 95% of all our weights will lie between minus 0.03 to plus 0.03. Look what happens. It gets squished, right? It gets squished to 0.5, minus 0.5 to plus 0.5. And we also plot the mean and standard deviation. So you see the mean and standard deviation. So the mean quickly goes to, let's say, for very quickly, the mean of the first layer. So we start with, let's say, around 0, and then the mean, it's almost around 0, right? Because that's how the data was. So the mean remains same because the weights are distributed around 0. So the activations are also distributed around 0. So the mean is fine. The mean is still around 0. And then look at the standard deviation. So the standard deviation has already come down to 0.05, which we can clearly see here. Yeah. And then after this we have a tan h. What is the tan h doing? It's squishing everything to -1 to +1, right? So that we have everything nicely in this boundary, in this range of -1 to +1. And then we apply the second layer with the second set of weight initialization, and very quickly look what happens, right? So the mean for every layer remains fine, which is 0, which is what we like, right? So this is 0, but look at the standard deviation. The standard deviation of the second layer is still something non-zero, but after that it collapses to just this one value, right? It collapses to just this one value of 0. So all my activations become 0 because of this weight initialization. And this weight initialization is actually one topic which did not receive enough importance, which did not receive enough, let's say, study that it merited, right? So, and this is the reason why we were not able to train these deep neural networks. So again, this weight initialization, though might sound trivial, is actually very important and is actually one of the reasons why we could not train these deep neural networks, because people did not pay enough attention to this weight initialization. And then what happened was, so all our activations became 0, right? And this is of course something we don't like. And then think about what happens when we do backward, right? Think about the backward pass. What would the gradients look like? So almost all neurons are completely, so all look, so you can, so this will be a quiz question. I want you to answer, what will the gradients of the loss with respect to the weights look like if all my activations have become 0, right? All my activations have become 0. What happens to my derivative of loss with respect to weights? Now so instead of using very small weights, let's use large weights. Let's multiply it by 1.0. So now we are actually sampling from this Gaussian with 0 mean and 1 standard deviation. So our weights will be distributed between -3 and +3, right? It'll be anywhere between here in a Gaussian shape, right? So there'll be more around the mean and then less around here. So this is what our weight distribution will look like. Now we do the same exercise, and again, because it's nicely distributed around 0, our mean is fine, right? Our mean is between, let's say, 0.008 to 0.0006. So we are fine with the mean, no problem with the mean. But look what happens to the standard deviation. The standard deviation is, it very quickly goes to almost to 0. Why? Because all our neurons get completely saturated to -1 or +1. And the gradient in this case will also be 0. Why -1 or +1? Because the weights either push them to a large number or a small number. And then these large or small numbers met Tanh, and then Tanh squished it to +1 and -1, right? Because that is what the Tanh looks like. You remember what Tanh looks like? A Tanh is a curve like this, right? And it's asymptotically approaching +1 and -1. So this is the y-axis. Y-axis is always the output, and this is our input, right? So our input, as the, so our input will, as long as our input will basically kind of give us this Tanh, which will kind of saturate to 1. Sorry, so this is not what it looks like. Obviously it looks like this, right? So no matter where our x is, our y is bounded between +1 and -1. So this is what Tanh is doing. Tanh is squishing my entire distribution to the edges, to this -1 or +1, and because of this all my gradients will be 0. So this is also something we don't like. And then Bengio and so this is the paper that these guys wrote, and I want to show you the paper first before I talk about how they did it. So this Javier Grolot and Joshua Bengio, they wrote this paper back in 2012, I would say, where they spoke about how to do this weight initialization right, and they called this paper Understanding the Difficulty of Training Deep Feed Forward Neural Networks. So why training these deep neural networks are difficult, and how can you do proper weight initialization. And it's a very cool paper, very easy to read. I would recommend you read this. But you see this equation 1? This equation 1 is what we will talk about in the slides. And they experiment. I mean, one of the basic assumption is that they kind of say that this is valid when we have this so-called linear activation layer, which don't mean anything, but just because we want to kind of add assumptions. So they don't put a non-linearity. They assume that everything is linear, and then they say that mathematically it makes sense to have this function. Or in other words, what they're saying is a reasonable initialization is when you have your random number, the random numbers between fan out and fan in. Fan out is the number of neurons as output, so this is your fan out, and the number of neurons as input, this is your fan in, right? So and this is your neural network. So what you want to do is you want to then sample between random numbers fan out and fan in, and you want to scale it by the square root of fan in, right? So this is what is most interesting, that you want to scale your weights by the square root of fan in. And this is something that was not in 2012, sorry, 2010 is when they published it, and this is one of the reasons why the deep learning revolution took off. This is one of the reasons why probably Bengio won the Turing Award along with Yan and Hinton, right? Because weight initialization, though might sound very trivial, is actually a very important topic to study. And then came ReLU, right? So this is something very interesting happened, and a seminal paper got published with making very little change. But somebody asked this question: what happens with ReLU? Is this Javier initialization still a good idea? And it turns out that the math doesn't hold. Why? Because look what ReLU does, right? So the ReLU kind of kills half my neurons, right? So the output of my layer is only half of them, right? Because if we initialize our, let's say, the initial layer weights around 0, then half the outputs, and we have normalized also our inputs with 0 mean, right? Because we've already done that pre-processing. So then half my outputs will be positive, half will be negative. And ReLU by definition will kill the half my activations. So I will only have the positive half left. And this positive half kind of breaks the math that we derived in the previous paper by Javier Grolot and Joshua Bengio. So what happens is, your mean very quickly goes to 0 after, let's say, 6 or 7 layers, and your standard deviation also approaches 0, and we don't like that, right? So if you do the math, and I recommend you check this paper out by Hay in 2015, but the intuition is very simple. All they are saying is, okay, you have a problem with this fact that we are reducing the activations by 2, right? Because we are killing half of them. Then multiply it by 2, put at 2 in the numerator, and the math actually holds. But somebody asked that question and the answer was so simple. So this is so elegant and I love this. And once you do that, look what happens. My mean is nicely maintained around 0.5 in this case. My standard, my standard, because why 0.5? Because the output is only positive, right? It's not there in the negative. If it was in the negative, then my mean would be around 0. It's around 0.5 because it's between 0 and 1, so the mean is around 0.5. And look at the standard deviation. The standard deviation is also nice and high, around 0.8, which is like around 1. So my my activations don't collapse like it collapsed here after, say, 6 or 7 layers. All the 10 layers, it's nice and proper. And this is the beauty of weight initialization and asking about these small questions. And these are, and training is also much better, and they kind of show that if you train with your Javier initialization, it doesn't train. You see the Javier initialization is this blue curve here. And if you train with their Kaming wrote this paper with the Hay initialization, it very quickly trains. So your loss curve is coming down nicely, but in this case it doesn't. And this is not the only two initialization, and initialization is just one line of code. Jan came up with his initialization when he came up with Tanh, because he realized that for this new activation layer Tanh, you need to do something different. Then this was earlier, then this is Javier's in 2010, then you have Kaming's in 2015. These are all part of, let's say, your framework, your PyTorch, your TensorFlow, your Torch Lua, everything. And it's just 2 lines of code, but those 2 lines of code make a world of difference when you train your neural network. And this is still an active research area. I haven't updated my slides too much, but let's say till 2017 there were people still studying what are the best ways to initialize your neural network. And as network get more complicated for diffusion models, for LLMs, we'll talk about later, weight initialization still plays a very critical role. And this is why we are talking about it, and I want you to get an intuitive understanding of why weight initialization is important and what is the goal of weight initialization. The goal of weight initialization is to have good statistics, a good mean, a good standard deviation, a good distribution of the activation values. We don't want it to collapse even when we go down the network, and that is all that we want to do with this proper weight initialization.